Welcome to Gooseberry Science and Education videos. I'm your nature guide for today, and along with our little orange gooseberry friend here, we're going to explore something pretty incredible. You know, life has this amazing, sometimes totally invisible, way of adapting to the world around it. But what happens when that world starts changing? Well, way too fast. Today we're going to see how nature's internal clock is getting reset by our warming planet, and how that's throwing a really delicate system into, well, chaos.
All right, so let's just jump right in with a question you've probably heard a million times. Are insects really cold-blooded? I mean, we throw that term around all the time, right? But is that really the whole story? Let's find out.
You look at a bee like this one, busy on a flower, and it's easy to think of it as this simple little creature whose body temperature just matches whatever the air is doing. But honestly, the truth is, the world of insects is just buzzing, no pun intended, with some of the most clever temperature control tricks in the whole animal kingdom. That cold-blooded label, it really doesn't do them justice at all.
And that brings us right to our first stop on this journey. We gotta forget about these insects being simple thermometers. The reality is, many of them are absolute masters of managing their own internal furnace. It's a process called thermoregulation.
So, the key to unlocking all this is a fantastic word, heterotherm. Now, unlike animals that are pretty much one temperature all over, a heterotherm can have, let's say, a toasty warm engine room while the rest of the body stays cool. And for an insect, this is basically their secret weapon.
So how does it actually work? Well, imagine you're a moth on a chilly morning. To get airborne, you can't just start flapping your wings. Nope. First, you've got to do a pre-flight warm-up. You vibrate those super powerful flight muscles without actually moving your wings. It's basically like shivering, and that generates a ton of heat. This cranks up the temperature of your thorax, that's the central powerhouse of the body, until boom, it's warm enough for takeoff.
And check this out. This quote from the entomologist Bernd Heinrich just nails it. He says, an insect's flight muscles are, metabolically, the most active tissues known. We're talking about a metabolic output that can be even higher than a hummingbird's. These are incredibly powerful tiny engines.
And the strategies they use are just, wow, they're so diverse. You've got butterflies that act like living solar panels, angling their wings to either soak up or deflect the sun's rays. Then there's the mosquito drinking warm blood. To keep from overheating, it actually releases a tiny drop of fluid and uses evaporative cooling. And maybe the most dramatic of all, Japanese honeybees. They'll defend their hive by swarming an invading hornet, and they all vibrate their muscles at once to literally cook the intruder to death. Insane, right?
Okay, so now let's shift gears a bit. We're moving from the super active world of insects to the seemingly still life of plants. I mean, they can't exactly shiver or go find some shade, so how on earth do they cope with a changing climate?
And the crucial thing to remember here is that plants are anything but passive. Over thousands, millions of years, they've become these perfect reflections of their environment. Their very structure, the shape of their leaves, how deep their roots go, it all tells a story of adapting to their local climate. They really are nature's silent barometers.
And this illustrates two totally different game plans perfectly. In dry, arid places, you get what are called sclerophylls. Think tough, leathery leaves that are designed to hold on to every last drop of water. But then you go to a warm, humid rainforest and you find epiphytes, like Spanish moss. These guys don't even need soil. They just hang out on other trees, pulling all the moisture they need right out of the air. Two completely different worlds, two brilliant solutions.
Okay, so we've established that plants and insects are absolute master adapters, right? They are incredibly fine-tuned to the world around them. But here's the big, pivotal question. What happens when the fundamental rhythm they're tuned to, the very timing of the seasons, starts to shift?
And this brings us to a phenomenon that scientists are tracking with growing concern. They've given it a name: spring creep. It's the steady, measurable, and pretty darn early arrival of spring.
The science behind all this is called phenology. You can think of it as the study of timing in nature. So phenologists are kind of like nature's timekeepers. They're out there recording when the flowers bloom, when birds migrate, when bears go into hibernation, basically creating this incredible calendar of life's biggest events.
So what are these timekeepers finding? Well, take a look at this data. It's pretty clear. In the UK, between 1992 and 2002, the first flowers started showing up 4.5 days earlier. In Spain, looking at data that goes all the way back to 1943, flowers were blooming almost 6 days sooner. And another UK study found that the whole cycle, leaves, flowers, and fruit, had jumped forward by almost a full week. This isn't just a fluke, you guys. It's a clear, documented trend.
Now, an earlier spring might sound kind of nice, right? More sunshine, but it creates a massive, massive problem. It's like throwing a wrench into the gears of a machine that has been perfectly synchronized for thousands of years. The whole system is falling out of sync.
And the core issue is right here. All those connections between species, predator and prey, the pollinator and the flower, they're all part of this incredibly delicate balance. But as temperatures rise, that balance starts to unravel, and the entire system, it just falls into disarray.
Let's look at a specific, and honestly a pretty heartbreaking example, the pied flycatcher. These birds have evolved to time their nesting perfectly, so their chicks hatch just when caterpillars are everywhere. It's an all-you-can-eat buffet. But warmer springs mean that the caterpillar peak, that big feast, is happening earlier now. The birds are trying to adapt, they're nesting earlier too, but they just can't keep up. So what's the result? The chicks hatch after the feast is already over.
And the consequence of this timing mismatch, it's staggering. In some woodlands in the Netherlands where this was studied, the populations of the pied flycatcher have crashed by as much as 90%. Let that sink in. A 90% drop, all because their food calendar is no longer lined up with their nesting calendar.
And look, this isn't just a bird problem. This is not an isolated story. We're seeing it with bumblebees that are struggling to keep up with earlier flowers. We're seeing it with species like the wall butterfly, where warmer autumns trick them into producing a whole third generation of caterpillars that hatch way too late to find any food. They literally starve before winter even gets there. It's called a developmental trap.
When you get right down to it, an ecosystem is a lot like this house of cards. Every single species is a card, leaning on and supporting all the others. A phenological mismatch, this timing problem we've been talking about, is like pulling one of those cards right out from the middle. The structure might hold for a second, but the whole thing becomes dangerously, dangerously unstable.
So what we're witnessing here is a fundamental change in the rhythm of life on Earth. The ancient dance between all these species is falling out of step. And that leaves us with a really critical question. As the timing of nature's dance falls further and further out of step, which of these connections, the ones so vital to the health of our entire planet, will be the first to break?